synthesis. However, I will do the dark reaction.
Because I'll know how many people
Not the one.
besides this class.
So a reminder that this survey is still available.
Yeah, right.
So far, the results are so far there's about a 50-50 split between doing them online with Adobe Connect and in person. Anyway, I would like to just say a little bit about the dark reactions, sort of token. I do want to discuss this enzyme. So remember, this is occurring in the stroma of the chloroplast. And remember, we sort of conceptually divided it into three phases. I want to say a little bit about this enzyme, Bisco. Last time I said it's the most abundant enzyme on the planet, so that suggests it's a kind of enzyme. So I would like to know that. So remember, when I introduced this last week, when I introduced photosynthesis, I think I sketched out what the dark reactions are. And it's shown in the slide, but the issue is to convert ribulose 1,5-bisphosphate to phosphoglycerate. So there's your ribulose 1,5-bisphosphate. So this is 5 carbons, so we have to add a carbon from carbon dioxide. So that carbon is going to be added at this position. And there's going to be an intermediate, which has this structure. So, and now this molecule, actually that's not quite the right structure. The intermediate is going to have this structure, where those 2 H's. And then that's going to be broken in half to break that carbon-carbon bond, and that's going to generate 2 molecules of 3-phosphoglycerate. So one of them is going to be these 3 carbons, the other one's going to be the lower 3 carbons. And then we sort of remember how to metabolize 3-phosphoglycerate by gluconeogenesis. And we'll maybe say a little bit about that. But this is the reaction that's catalyzed by this enzyme Bisco, ribulose bisphosphate carboxylase/oxygenase. I'm only going to discuss the carboxylase, not the oxygenase reaction. So the issue is, first of all, how do you form this intermediate? How does this enzyme enable a carboxylate group to be added to this compound? So we've seen reactions in which we carboxylate things, and we always have started with bicarbonate, and we used biotin and ATP. So none of those are involved in this reaction. This is a chemically much simpler reaction. The reaction goes as follows. So we know that CO2 is an electrophile, and so we're going to make a carbon-carbon bond up here. And so typically we're going to have a nucleophile that's going to attack this electrophile. So we need to get a nucleophile out of ribulose 1,5-bisphosphate. And so the way that that's done is This proton is relatively acidic because it's next to this carbonyl. And a base on the enzyme is going to remove that proton, and we're going to form an enediol intermediate, like we've seen for some other reactions. This is some different one. The base on the enzyme is actually, interesting, the lysine side chain. But that lysine side chain is itself carboxylated. So this is called a carboxylamide. Or this is a carbamylated lysine side chain. And the way that you carbamylate, these are not the jokes. Not at an inappropriate time. So if you imagine, let me leave it at stage 2. This actually reacts with bicarbonate. And this place. So that comes from, so this is a lysine. It actually has to be activated. There's a separate enzyme that catalyzes insertion of this carboxylate group onto this lysine. As long as the rubisco has the carboxylate, it's active. So it gets activated and then it can catalyze reaction. And so this is now going to be the base that's going to pull off this proton. So this is going to grab a proton and will generate, there's some acidic group in there that's going to protonate that oxygen. But this is going to make an enediol like we saw for our isomerase reactions long ago. And so there's the ene, the double bond. Now that you think of those two electrons in that double bond can then be used as a nucleophile. Nucleophile uses electrons. To generate the nucleophile, there's a base, which I think is a histidine bonus. There's a base. It's going to grab a pair of protons, or grab a proton, and you could put the electrons onto that carbon temporarily. So there, I've drawn this as an intermediate, just explicitly to show a carbanion, but the carbanion is going to react with now carbon dioxide, and again, this is CO2 just in solution. And so this is a nucleophile reacting with the electrophile, and that's going to give us the intermediate that I drew in the first place, which is this. So we have a new carbonyl. And now this molecule can be broken in two. And so to break this molecule, we can use the carbonyl. And so the enzyme will catalyze nucleophilic attack like water on the carbonyl. We could make a tetrahedral intermediate, and then two. And the bottom part will get carboxylic acid, will ionize. So this is a proton there just to balance it.
So the carbon dioxide, that's
Yes.
independent of the...
Yes. It's interesting that the enzyme has to, bicarbonate, CO2 has to be there for the enzyme to be active, but then this is a separate reaction. And And again, this enzyme will catalyze many reactions like any enzyme. All right, so let's see. We've broken off these 3 carbons. That's one of the 3 phosphoglycerates. The other one, all we need to do is protonate it, finish the reaction. Draw it that way, and you take the leaving group, which is carbanion. This carbanion is stabilized by the adjacent carboxylate group. I'll show the picture from the book that shows a magnesium ion that's also going to be helping. But this can then just grab a proton, and that's going to give us the second molecule of 3-phosphoglycerate. All right, so it's kind of an unusual reaction. Combines some chemistry we've seen before. Sorry, which this is water. So maybe for consistency. Here's the picture from the book, which is essentially, as I've shown it, they push the arrows a little bit. This stuff they show the arrows in slightly differently than I did, but it's the same chemistry. It does emphasize. So here's a lysine with a carboxyl group on it. And here's a magnesium ion in the active site that's going to help to neutralize some of these intermediates, especially down here. That's going to help stabilize the carbanion intermediates. But basically, I think the stuff's already there. So this is this reaction. Rubisco. This is the enzyme that makes all the carbohydrates that exist on Earth. Okay, so once we've got 3-phosphoglycerate, then as I again sketched out last week, we've seen a lot of ways that a cell can use this. The cell, so on this slide, they're emphasizing making glucose or cellulose, whatever it might be. But this could also be used in glycolysis to make acetyl-CoA, to make fatty acids pathways that we'll cover soon. So this is, as I've indicated, to get from 3-phosphoglycerate to glycerolate 3-phosphate is just gluconeogenesis. And remember, though, this requires use of an ATP to make the 1,3-bisphosphoglycerate. And it requires reduction. In this case, it's an NADPH to reduce the carboxylates to the aldehyde and to make glycerolate 3-phosphate. But this is stuff that we've seen before. So I don't need to really say anything about the gluconeogenesis. Let's think of the gluconeogenesis, or at least they've indicated that we've gotten this far to glycerolate 3-phosphate. Glycerolate 3-phosphate, of course, can be used to make glucose 6-phosphate, which is used to make starch, and so on. So the gluconeogenesis would continue by this arrow. This arrow up here is what they're calling stage 3. And I want to say a little bit about stage 3, but without going into all the details. So, as I also indicated last week, this cycle begins with 0.3-bisphosphate, ribulose 1,5-bisphosphate, and we have to regenerate that. And I went through the stoichiometry that, if you started with 6 of these 30 carbons, we'd end up with plus 6 CO2s, we'd end up with 12 3-phosphoglycerates, right? We're going to use 10 of the 3-phosphoglycerates to regenerate ribulose 1,5-bisphosphate. Although the stoichiometry will work out is if we take 5 molecules of glyceraldehyde 3-phosphate, so that's 15 carbons, we can use those to make 3 molecules of 1,5 ribulose 1,5-bisphosphate. All right, so this pathway is one that we haven't seen, but we've seen something rather similar. So here's the complete pathway. And So the ribulose 1,5-bisphosphates are there. That's two of them there, actually. And the third one is down here. Right? And the glycerolate 3-phosphates, if you examine this figure carefully, you see that there are three of them. And then the other two molecules of glycerolate 3-phosphate have to be made into dihydroxyacetone phosphate. So that accounts for 15 carbons that are coming in. And all of these could have been glycerolate, but they arose from glycerolate 3-phosphate, which arose from the 3-phosphoglycerates. So the question is, how do you put all these things in? Put these 5 molecules in and get these 3 molecules out. And so this is this very convoluted sequence of reactions, which I'm not going to go into any detail on, but I just want to point out that this enzyme transketolase, which occurs twice, is an enzyme that, and also some of these other enzymes, this ribulose 5-phosphate epimerase, ribulose 5-phosphate isomerase. Those are all enzymes that are part of the non-oxidative phase of the pentose phosphate pathway. So we saw for the non-oxidative phase of the pentose phosphate pathway that you could take intermediates of glycolysis and you could use them to make ribulose 5-phosphate. Right? So the intermediates of glycolysis were fructose 6-phosphate, 2 of them, and the glycerolate 3-phosphate. So again, 15 carbons. And these fructoses could have come from glycerolide. Right? So this is essentially the equivalent to what's happening with dark reactions. Here's transketolase acting twice, right? And then here's that isomerase and epimerase. So these enzymes are the same enzymes from the non-oxidative phase. And so these reactions, which I didn't go into any detail on, are essentially the same as were shown in the previous slide. Now there is one difference. This enzyme transaldelase in this particular reaction, which if we're going to the left, would make the 7-carbon acetoheptulose 7-phosphate and glycerolate 3-phosphate. This reaction actually does not occur in the dark reactions, in the catalyst. So let me just go. Oh, and the other thing about this is, remember, the stoichiometry of this is that we could start with 2 6-carbons and a 3-carbon here, and we could use those to make 3 5-carbon ribulose 5-phosphates. Right? So it's the same stoichiometry as we need for the catalyst. So there's one of the transketolase reactions. This is the same reaction as in the pentose phosphate pathway. So one of the fructose 6-phosphates plus glycerolate 3-phosphate is converted to erythrose 4-phosphate of 4-carbon plus the 5-carbon xylulose. This can be converted to ribulose and then phosphorylated. So that pretty much is where we need to be. This 4-carbon is really next. Right, so there's transketolase. Here's the other transketolase reaction. Again, this is the same reaction as on the previous slide. Take the 7 carbons plus 3 to make 10, break it in half to make 2 5-carbons. And again, you can make both of those into the ribulose. Well, you can make both into ribulose 5-phosphate and then phosphorylate. Right, so those again are the same 2 reactions as on the previous slide. There's 2 reactions that are different, at least 2. So one of the steps in this pathway is making fructose 1,6-bisphosphate. That's just the aldolase reaction, right, from gluconeogenesis or glycolysis. And then the next step of that is hydrolysis by fructose 1,6-bisphosphatase, also a gluconeogenesis enzyme. And so that makes the fructose 6-phosphate. That reaction is somewhat significant because it's an irreversible reaction. Right? It's hydrolysis of a phosphate ester. To go from here to there to regenerate the fructose 1,6-bisphosphate, you have to use ATP. So this is an irreversible step. This is not really one of the steps of the non-oxidative pentose phosphate, so it's a little bit different. And it helps to make this whole process irreversible. Having this additional, in some way, an extra step makes this irreversible. The other step that's irreversible is a new step, and this is one where this is a sort of chemistry we haven't seen, which is a reaction also catalyzed by aldolase. So this is the same aldolase that catalyzes this reaction. And either way, it's going to use dihydroxyacetone phosphate. But in this case, the other substrate is erythrose 4-phosphate. So normally in glycolysis or gluconeogenesis, it takes aldolase takes 2 3-carbons, puts them together to make a 6-carbon product. Here it's taking a 3-carbon, but now a 4-carbon sugar, and it's putting them together to make this cetoheptulose, but this is cetoheptulose 1,7-bisphosphate. And this is not an intermediate in the pentose phosphate pathway. So this, in that respect, this reaction is new. And this is also significant because the very next step is hydrolysis of one of the phosphate esters in here by this new enzyme, cetoheptulose 1,7-bisphosphatase. So we have a second phosphatase, and you have a second irreversible step, right? And so you have that irreversible step that makes cetoheptulose 7-phosphate, and then the rest can continue. So these 2 steps are irreversible. Everything else is reversible, like it was in the pentose phosphate pathway, with the exception of these final phosphorylation steps. So I think these steps are important because for the plant always wants to make this stuff by this pathway. And pentose phosphate, I sort of pointed out that it could go either way. It depends on what the cell needs. You need that material. But here the plant always wants to make this. So in the plant it's important. That's the rationale for having these additions.
So are either of these 2 steps or both what are metabolically regulated?
I don't, not as far as I know. All right, so that's really all I want to say about this very complicated network of reactions. And so just like for the pentose phosphate, I sort of said, you need to know the details on that. So instead, I would like to say that we finish, I guess, box these last steps, so we have to remind you that we need to make ribose 1,5-bisphosphate. So we do have those 2. So remember, we're using a lot of ATP in this process. All right, so that's all I'm going to do in photosynthesis in the interest of time and in the interest of moving on to other things. So if there are any questions, now's the time. Otherwise, we'll move on. So I did a little bit of chapter 20. Now I want to spend the next few classes on fatty acids. So we did a lot of redox chemistry and a lot of photochemistry. So now we're back to just plain old organics, which is good. So just remember what fatty acids are. So fatty acids are carboxylic acids. The most common ones have even numbers of carbon atoms, so we have a carboxylate group and then some number of methyl E groups. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 16. This is the 16 carbon fatty acid. This is called palmitate. Palmitate is a saturated fatty acid, meaning that there are no double bonds in this hydrocarbon chain. And palmitate is the only one that I'm really going to discuss. Right? So there can be longer fatty acids that have 18 or 20 or 22 carbons. Their metabolism has some variations on what I'm going to discuss. I will not go into longer ones. I will also not do anything about unsaturated fatty acids. So I just want to focus on plain old saturated fatty acids. And so the first thing I want to discuss is how these are oxidized, how they're catabolized. The oxidation of fatty acids, the pathway is known as the beta oxidation pathway. So that's what I'm going to at least introduce today. Let me remind you, let's go back to this diagram that we did a while, but we did all this stuff with glucose, glycogen, pentose phosphate, citric acid, etc. And remember that fatty acid metabolism is going to either start with or end with acetyl-CoA. And so just as acetyl-CoA can be made from pyruvate, acetyl-CoA is made from oxidation of fatty acids as well. So this is the beta oxidation pathway, takes this, say, 16 carbon fatty acid and breaks it into 8 molecules of acetyl-CoA. So all 16 of the carbons will end up as acetyl-CoA. Now, the biosynthesis of fatty acids also begins with acetyl-CoA, and so the carbons in the acetyl groups can be used to make fatty acids in a separate pathway. As we'll see, there's a lot of parallels between these two pathways, but they are completely different enzymes. So again, I'm going to be doing the beta oxidation pathway today. This is a figure that shows oxidative metabolism and respiration. So again, glucose, pyruvate acetyl-CoA. Fatty acids are also oxidized to acetyl-CoA. Lots of electrons are taken out. They're collected in NADH or FADH2. And all of this occurs in the mitochondria. So fatty acid oxidation is entirely in the mitochondria. Now, where do we get fatty acids from? We get fatty acids from fat in our diet. So fat, of course, is triacylglycerols. So that's so the fat that we eat, we digest it in our small intestine, and there are intestinal lipases, and they catalyze hydrolysis of these ester linkages. So remember, triacylglycerol is glycerol, 3 carbons, esterified to 3 fatty acids. So lipases just catalyze hydrolysis, catalyze nucleophilic attack by water on the esters, and displace glycerol. So the product of this hydrolysis is that you get 3 fatty acids plus glycerol. These are formed in the small intestine. They're both taken up by the cells that line the small intestine. There's fatty acids. They're amphipathic molecules, but they have these long hydrocarbons, so they're not very soluble in water. And so there's a whole transport mechanism to carry these things around in the body and avoid having them form clumps and aggregates. And I'm not going to go through any of that. It's kind of interesting. It involves high density and low density lipoprotein particles, HDL, and so on. But those are ways to carry these fatty acids in the bloodstream. Glycerol is extremely soluble in water. Glycerol, let me just sort of say, without going into detail, glycerol is metabolized, and it's metabolized in 3 steps to make dihydroxyacetone phosphate. And now once it's been made into dihydroxyacetone phosphate, that can be metabolized in any way that DHAP can be metabolized. So for example, glycerol can be used, the carbons in glycerol can be used to make glucose. They can also be oxidized by glycolysis. So you can certainly use the glycerol that comes from that. But the focus is again on fatty acids. All right, so dietary fat is used in that way. We also store fat. store fat in adipose cells and adipose tissue. And so when we need to use that stored fat, we also have lipases that function in the adipose cells. And this is shown on this picture from the book. So this is supposed to be, yellow is an adipose cell with a big fat globule in the cell made of triacylglycerols. And the lipase in these cells is called hormone-sensitive lipase. And so it's an enzyme which, it's a lipase. It catalyzes hydrolysis of these ester linkages, so it produces fatty acids and glycerol. Those fatty acids are released into the bloodstream, and they can be taken up by other cells. So this hormone-sensitive lipase catalyzes the same hydrolysis reaction. It's called hormone-sensitive lipase, and so my non-quicker question is, which hormones? So this is stimulated by hormones. Right, so which hormones stimulate this? Right, remember there's only 3 hormones. What are the 3 hormones? Insulin, glucagon, epinephrine. So which ones can stimulate this? Glucagon, epinephrine. So glucagon, is when you're starving. So that's when you break down fat. Insulin is when you're well-fed or overfed. That's when you make fat. So insulin is going to inhibit this enzyme, and glucagon and epinephrine are going to stimulate it. So they show glucagon up here. These other hormones are also involved. Glucagon is the same stimulation of glucagon stimulates formation of cyclic AMP, which I think I say. So that's the same simple fat. Okay. So either way, we can take fatty acids from fat in our food, or we can take it from the stored fat that we have. And the fatty acids are released into the bloodstream, and they're carried around one way or another. And in this picture, they're showing a muscle cell, a myocyte, which is able to take up fatty acids from the bloodstream. And so muscle cells will use fatty acids, and we'll be able to oxidize them, and other tissues as well. But note that brain cells and nerve cells can't take up fatty acids. They don't have the transporter, so brain cells will not use fatty acids. Will not be able to do beta oxidation of fatty acids. But muscles will, and other tissues.
Is there like an evolutionary reason for why?
It doesn't seem like a very good idea, but I don't know if there's an evolutionary reason for that. I don't know why shouldn't the brain use that? It just comes up.
Just trigger them.
Oh,
Yeah, there's a really strong
yeah,
selection.
right, of what goes in. But why didn't it allow this?
It's like really very, very specific.
Yeah. Well, be that as it may. Let's focus on what happens in muscle cells. So,
You say that? Say what?
let's say this is a muscle cell. And so fatty acids, this is blood.
He said, I don't know how.
And within the muscle cells, the mitochondria. So beta oxidation, as I said, occurs in the mitochondria, in the matrix of the mitochondria. And beta oxidation process involves the following overall reaction. So the fatty acid is oxidized when in the form of an ester to coenzyme A. So this is called a fatty acyl CoA. And so the beta oxidation process is called beta because it involves oxidation of a beta carbon. Right? So using this as our sort of reference, this is alpha, that's beta. So the beta oxidation pathway is going to involve oxidation of the beta carbon to a carbonyl. And that's going to allow that carbon-carbon bond to be broken in the reverse of a reaction of the type that we've seen already several times. And I'll go through the details Monday. But the bond is broken in a reaction that involves nucleophilic attack by CoA on this carbonyl. And the result is that you get a new fatty acyl CoA, which is 2 carbons shorter than this one. And if I'd been more careful, I would have counted my carbons. But these 2 carbons and the original CoA are going to be released as an acetyl CoA. So that's the overall process that has to happen. You have to oxidize this carbon to carbonyl, and then you can break off that carbon. You can break that carbon bond and produce an acetyl CoA. So if 2 of the carbons are gone, the remaining, say, 14 are in the form of fatty acyl CoA, which is just 2 carbons shorter. Oxidize this beta carbon, which in my drawing, that's the beta carbon. So you do a second cycle of beta oxidation, split off these 2 carbons as a second molecule of acetyl CoA, and so on. Okay? So it's a cyclic series of reactions. I'm going to go through the details of those reactions in a minute, but I've sort of skipped two important steps. So let me go back to this original drawing that I made. I'll do all this again. So here's the issue. I skipped 2 things. First of all, we have a thioester of the fatty acid CoA. And so where did that come from? So that turns out to be formed in the cytoplasm.
That's what the cell is.
So the fatty acyl CoA is made in the cytoplasm, and then that molecule has to get into the mitochondria. Now you might think there'd be some transport mechanism that would just take this thing into the mitochondria, but of course life is never that simple. Because the idea is probably that the cell wants to have some CoA that's always in the cytoplasm, and it wants to have some CoA that's always in the mitochondria. And so rather than shuttling CoA in and out, there's a separate transporter, which I'll say a little bit about. And that transporter involves a molecule called carnitine. And carnitine is a molecule that enables the fatty acid, that's a fatty acyl CoA, enables the fatty acid part to get into the mitochondria and be regenerated as it attaches. So those are the 2 things I want to discuss. I want us to say a few words about this reaction. How do you make the fatty acyl CoA? And then I'll just show you the structure of this and a little bit about how it actually gets in. So the first issue, again, is to take palmitate. So 1, 2, 3, 4, 5, 6, 7. There's 16 carbons. So that's palmitate. And this has to react with CoA, with the thiol group CoA, to make palmitoyl CoA. And the other product is water. So this is a condensation reaction in which the thiol group reacts with the carboxylate group to make a thioester, and you make water as the other product. All right, so what do we remember about thioesters?
High energy.
Nothing.
High energy.
Yes, sorry. Yes.
Is that supposed to be 16
I made 16, so if I might have miscounted. But I did want it to be 16, and you have to include this one. So that's palmitate. So that's I'm just going to take palmitate. So what do we remember about thioesters? So what we remember is that these are high energy compounds. So what's the delta G approximately? Delta G is our prime for this reaction as I've drawn it. It's about plus 30, roughly. All right, so that reaction is not going to go spontaneously. You can't just put these two things together. And this is actually a very common kind of reaction in metabolism of trying to take a carboxylate group and make it into an ester or some other type of molecule. Carboxylates are very stable because of their delocalization of electrons. So you have to sort of activate the carboxylate. And you could say you have to activate it thermodynamically as well as kinetically. So what molecule are we going to use to enable this thing to go, this reaction to go spontaneously to the right? Of course, we use ATP. So the reaction that the enzyme that catalyzes this reaction is called fatty acyl-CoA synthetase. And so the reaction begins by the P with a circle. Okay. So there's ATP. And the reaction involves nucleophilic attack by the carboxylate group on the first phosphoryl group, that's the alpha phosphate. And it displaces pyrophosphate in the process. And so you get just an intermediate, the fatty acyladenylate, which I'm not drawing all the carbons, obviously. So this is AMP that's been joined to the carboxylate group. What kind of a linkage is this? I'll ask that question in a week. This is a mixed anhydride, so it's a high energy bond in that sense. And the other product is, of course, pyrophosphate. Okay, so this is now thermodynamically and as well as kinetically active. There's a good leaving group, and it's a high energy intermediate. So this can react with CoA, again catalyzed by the enzyme. So base is going to grab this proton, and the sulfur attacks the carboxylate file. Tetrahedral intermediate, and displace AMP, and this makes the palmitoyl CoA thioester plus AMP. And so to make the thioester, we needed 30 kilojoules of free energy. Remember how much free energy you get by taking ATP and splitting it into AMP plus pyrophosphate, which is this. Remember that you get actually even more free energy than if you just hydrolyze ATP to make ADP. Remember, this reaction has a delta G0 prime of about minus 45. So that's enough energy to make the thioester. Yes?
What does the term synthetase mean?
Let me address that question. No one's ever asked. Let me just remind you about what happens to pyrophosphate. Remember that, of course, there's the enzyme pyrophosphatase, which catalyzes hydrolysis of pyrophosphate to make two phosphates. And remember the delta G0 prime of this reaction? It's about minus 19. Right, so in the cell, the pyrophosphate is also being hydrolyzed. So there's a very large free energy driving force for this reaction. That's how you overcome this process. So what's a synthetase? I think it's discussed somewhere in the book. There's synthases and synthetases. Synthetases use ATP to make things. So a synthase makes things, but it doesn't use ATP to make it. So ATP synthase makes ATP, but it doesn't use ATP to make it. Synthetases always use ATP. Succinyl-CoA synthetase uses GTP, but it's the same. So that's okay. So this happens in the cytoplasm. But now we've got the palmitoyl-CoA, the thioester, and again, this is the substrate for the beta oxidation process. Okay, so here's the reaction, the figure in the book that shows what I just drew on boards, made through the pyrophosphate reaction. So now to get the fatty acid into the mitochondria, this is where this molecule of carnitine comes in. And so here's the figure from the book that shows this is a matrix of the mitochondria. This is where the beta oxidation is going to occur. Here's the cytoplasm, so there's where the fatty acyl-CoA is made. And what's indicated on this figure is that the fatty acid group is first transferred to carnitine to release the CoA and make now an ester of the fatty acid esterified to carnitine. That is what is actually transported into the mitochondria, where the fatty acid group is transferred back to a CoA to make the fatty acid. So it's the carnitine that gets transported in and out, and the CoA is always stays on this side or stays on this side. So again, why evolution chose to do this way. But that's where carnitine comes in. Carnitine, here's the structure of carnitine. I won't have to memorize it, but this OH group is what is going to enable to form the ester with the fatty acid. So you're going to have a fatty acyl-CoA and carnitine is going to catalyzed by an enzyme. So carnitine has this hydroxyl group that's going to displace the CoA, and you're going to get an ester of carnitine with the fatty acid.
Yes.
And this is the thing that is being transported into the mitochondria. So when you go to a health food store and you can find bottles of carnitine, this is why you need carnitine. Now, whether eating more carnitine is going to help you do this faster, I don't know. But so that finally produces the fatty acyl-CoA in the matrix of mitochondria. Where is the oxidation? Questions? On my black bag there, I have the exams.